All right, last class we got into some heat capacity stuff and temperature change. So we were learning about things especially related to this Q equals mc delta T, where C is our specific heat capacity, and the reason that this says specific is because it's for 1 gram of a material. So how much energy does it take to raise the temperature of 1 gram of material by 1 degree Celsius? Would also be the same as 1 Kelvin. And this is an intensive property, C is, and so we can use it to identify different elements or materials. And these are values that we would typically look up. The only one that you might want to memorize is for water, which is 4.184. It sort of depends on the temperature as well. And we've got our change in temperature term here, that's temperature final minus temperature initial. You're likely to not get this Q equals mc delta T on an exam. It's a good one to know. And so we're going to be going into more details about Q equals mc delta T and other ways that we can transfer energy. So if we've got two objects at different temperatures, so like a hot object and a cold object, and we put them together, the heat, the thermal energy, is going to flow from the material at the higher temperature to the material at the lower temperature. Hot objects transfer heat to cold objects. Heat is going to flow until both materials reach the same final temperature. Cool, I was just getting some deja vu, so I wasn't sure if we'd cover this yet. It's going to flow, heat or energy is going to flow, thermal energy will flow until they reach the same final temperature, and then no more energy is going to flow because they're at the same temperature. They have the same thermal energy. The amount of heat energy lost by the hot material is going to equal the amount of heat gained by the cold material. We're assuming that we've got a perfect transfer of heat. This is normally not the case, but we can get pretty close in some circumstances. So all of the heat energy is going from the hot thing to the cold thing. And so if our system is one of the things, then the heat that's gained by our system, remember Q is heat, heat gained by system is going to be equal to the heat lost by the system. That's the Q sys equals negative Q sir. Or the heat gained by one object is equal to the heat lost by another object. I'm saying heat gained here for this one because it doesn't have a negative sign, so it's positive. It's a heat value put in. And for our Q surroundings, it's negative because it's negative, so that's heat loss. For example, if we take a block of metal at 55 degrees Celsius and we plop it into some water at 25 degrees Celsius, our metal is hotter, higher temperature than our water, and so energy is going to flow from the metal out into the water. This is sort of the opposite of putting ice into your water. When you put ice into your water or a drink, the ice is cold, and so heat energy flows from the water into the ice. So that'd be an example that we probably have some familiarity with. So the heat from the metal is going into the water. And the temperature change is going to depend on a couple of things. One of the things that it's going to depend upon is the mass of the metal, the identity of the metal, and specific heat capacity. It's also going to depend on the amount of water that we have. So here we're taking Q metal equals negative Q water, and we're expanding, we're subbing in. Since Q equals mc delta T, we can sub in mc delta T on both the left side and the right side, and we can do calculations with it, which I think we'll be doing some today in our lab. So let's say that we've got a block of copper. Copper is an important thing to know here. So we've got copper. We don't know the mass of the copper block. It's got an initial temperature that's given to us. The copper is immersed in or put into a beaker that's got some amount of water at a given temperature. When the two substances reach thermal equilibrium just meaning they're the same temperature, the final temperature is 24.2 degrees Celsius. We could calculate, and we're going to do that, the mass of the copper block. So Q water, our water starts at 22.7 degrees Celsius, our metal starts at 65.4 degrees Celsius, and they both go to 24.2 degrees Celsius. So for the water, it went from 22.7 to 24.2. That's an increase in temperature, so our water is gaining energy. So I'm writing it as QH2O. The amount of heat that our water must have gained came from our copper. So I'm writing negative Q copper. It doesn't really matter which one's positive or negative for the sake of solving the algebra. So we can substitute in MC delta T for both of these. So we're going to do that. Q equals M water times C water. I'm going to actually switch to using W instead of H2O just because it's shorter. Equals negative Q copper, which is the mass of the copper times the C value for the copper, the specific heat capacity, times the delta T for the copper. And we can expand the delta T. So sub in TF minus TI. So whatever our final temperature is, in the case of our water, it's higher than our initial temperature. And the same thing is going to work for our copper. Okay, so let's look through and figure out what we have. So we're looking for the mass of the copper. We're asked to find mass of the copper block. Do we have the mass of the water? Yes, we have the mass of the water. Do we have the C value for the water? We do not have the C value for the water, but it's a C value. We can go look it up, or we can be provided it, or maybe we've memorized it. So 4.18 joules per gram degrees Celsius. So we'd get that from a table. That's something that we can find. Do we have our final and initial temperatures of water? Yes. We have those. We don't have mass of the copper because that's what we were asked to find. Do we have C copper? We don't have C copper, but we can get it from a table. So let me go sneak back to this table. Boom. So copper here, 0.385. Going back. Okay, so 0.385 joules per gram degrees Celsius. We also have our final temperature and our initial temperature of the copper. The final temperature for them is the same at 24.2 degrees Celsius. So you've got a couple options when solving problems like this. We've got a lot of variables, and so it might be easier, it might be more convenient for us to just, let's throw all of our numbers in, multiply everything on the left side, multiply everything on the right side, and then we've got two numbers, and then we'll swap them around. So we'll do that approach. You could also do a more pure math approach where you just shuffle all your variables around until you get it solved and then plug your numbers in. Either way, you'll get the same result. So we're going to plug in our numbers. So our mass of our water, 95.7 grams from the problem. Our CW, 4.18 joules per gram degrees Celsius. TF minus TI, which is 24.2 degrees Celsius minus 22.7 degrees Celsius, putting that in parentheses so we make sure that we do that first. And then On the other side, we've got negative mass of the copper times C copper, which is 0.385 joules per gram degrees Celsius, times TF minus TI, 24.2 minus 65.4. Do we have any questions about that so far? Okay. And then it's calculator time. So on the left side, we are going to do all of this, multiply it all out. So 95.7 times 4.18 times, open parentheses, 24.2 minus 22.7, optional close parentheses. The left side boils down to 600.039. Our units of grams will cancel, our units of degrees Celsius cancel. The ones inside the parentheses don't cancel. They cancel when we multiply with our C value. So this has units of joules. On the other side, we're putting in 0.385 times, open parentheses, 24.2 minus 65.4. We get a negative value. So we get a negative value because we've got 24.2 minus 65.4. That's going to give us a negative number. That negative we can use to cancel out this negative. So I'm going to rewrite this as mass copper times the number that we got, which is 15.862. And the units that cancel are going to be the degrees Celsius. So this will have units of joules over grams. And then our last step, divide both sides by 15.862 joules per gram. That will make the joules on the left side cancel out, and these grams will flip to the top. So mass of copper equals 37.8 grams, somewhere around there. All right, so that's some more Q equals MC delta T stuff where we're doing heat transfer. We're going to be doing heat transfer today. There's other related processes. So one of them is pressure volume work. You may remember we talked about internal energy, E, last class, and internal energy is the sum of heat and work, Q and W. One type of work that we have is pressure volume work. The pressure volume work occurs when a force caused by a change in volume acts against an external pressure. So anytime that we're expanding something and there's pressure outside, there's some amount of work that is put into that. So an example would be like a combustion engine. We're blowing something up, we're causing a rapid expansion inside of the cylinder, and it's forcing the piston to expand, to push out, and there's pressure outside. So in the process of pushing, right, we have to displace stuff, there's some stuff that's going on when we're expanding there. And so there's work being done when that happens. So when gases expand, our change in volume is positive, but the system is doing work on the surroundings. So the system is doing work. Anytime that you do work, you are exerting energy. And so the work is negative external pressure times the change in volume. So this is another important work equation, energy equation. And to convert the units of pressure and change in volume to joules, we can use this conversion factor. 101.3 joules equals 1 atmosphere times liters. So now we can do calculations about if a gas is expanding, how much energy is it using, how much work is it doing in that expansion process. So we've got a cylinder equipped with a piston. It expands against an external pressure. Work equals negative P external delta V. And 101.3 joules equals 1 atmosphere times liters. Okay, so a cylinder equipped with a piston, so it means that it can expand, it can change volume, expands against an external pressure of 1.5 atmospheres. So external pressure 1.58 atmospheres, that's P sub EXT, 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work was done? So we got some volume values. And as is often the case, it's helpful for us to write these out just so we can keep track of them without having to parse through all the text again. This delta V is the change in volume. That's our volume final minus our volume initial. That I looks weird. That's better. Okay, so let's find out how much work was done in joules. So we get W equals negative external pressure, 1.58 atmospheres, times our change in volume. Our final volume is 1.245 liters. Our initial volume was 0.485 liters. So to find out how much it changed, we'll just subtract those two. So work equals negative 1.58, and plug the rest in. We get a value of negative 1.2008. Is that our final answer? What are the units of the work that we calculated? The units here, we subtracted liters, so we'll still have a value of liters here. We multiplied it by atmospheres. So the units here are liters atmospheres. And the question asked for work in joules. So we need to convert from liters atmospheres to joules. And we do that with this conversion factor, 101.3 joules equals 1 liter times atmospheres. So multiply by 101.3 joules over 1 atm times L. So multiply by 101.3, and the work is actually, in joules, negative 121.6 joules. So we'd probably round that to 122 joules. So what this means is that the cylinder did 122 joules of work. It lost 122 joules worth of energy by expanding. All right, we're going to build a little bit. So we're going to rope back in our change in energy, our delta E concept. So when fuel is burned in a cylinder equipped with a piston, so its volume can change, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is the change in energy for the burning of the fuel? So we've got two separate things going on here. It might be helpful for us to remember what delta E is. So E for energy, delta or triangle for the change in, it's our work plus our heat, but our heat is the Q and our work is the W, so I set them in the wrong order. So heat plus work. We were given the heat, it's 875 joules. So Q equals 875 joules. We need to ask ourselves, is it a positive or a negative value? Negative value. Why is it a negative value? It's being emitted. So since the heat is being emitted, that's heat that's being lost. So it's emitting heat, and so our Q value is negative. And then we can calculate with our change in volume and our external pressure what our work is. So we're going to find work. It's negative PEXT delta V. So negative 1.02 atmospheres times final volume minus initial volume. So 1.45 liters minus 0.255 liters. So our work plugging it in, negative 1.2189 liters atmospheres. And again, we need to multiply, convert to joules. So we multiply by 101.3. So it's negative 123 with some other numbers, joules. So we've got our Q value, we've got our W value, and for our change in internal energy, our delta E, we just add those two values up. So negative 875 joules minus or plus negative 123 joules. So the work that we did, or the work that our fuel did, is 990, wrong color, 998 joules. And it's negative. Questions? I'll probably give you this work equals negative P external delta V. I'll definitely give you this 101.3 joules conversion factor come exam time. Okay, so that's a calculation that we can do for delta E. We can also measure delta E. So we can measure our change in internal energy for different processes. So a system is going to exchange energy with its surroundings via both heat, so we were looking at that before, transfer of thermal energy outward or inward, and also pressure volume work, assuming that volume can change. So these are two ways that we can transfer energy with our surroundings: pressure volume work and heat. There's a couple of ways that we can measure heat and work. One of the ways that we can measure change in internal energy is with constant volume calorimetry. So the change in internal energy, our delta E, when we're doing a chemical reaction, is a measure of all of the energy exchanged. Right? So delta E equals the heat plus the work. And we said previously, right, so Q, we've got MC delta T, so we can exchange heat. With our work, we only know about pressure volume work. And so the work here depends on volume changing. If volume doesn't change, if delta V is 0, then work equals 0. So if we can create a system where our volume can't change, where we've got rigid walls, then our change in energy, our change in internal energy, is going to be equal to our heat value, because we know that no work was done because no volume change occurred. So QV is heat at a constant volume. The V here meaning that we have constant volume. Q still being heat. So constant volume calorimetry is a way that we can measure our change in internal energy. It's not practical to observe temperature changes of individual chemicals in a reaction. Instead, we can measure a temperature change using an insulated, controlled surroundings, like in what's called a bomb calorimeter. And we'll see an image or a diagram of what a bomb calorimeter looks like. So in a bomb calorimeter, volume is constant. And so the change in heat of our system is equal to the negative change in heat of the surroundings, which is the same as our calorimeter. So we're basically creating an environment where we're catching all of the heat from a reaction that's going on inside of that. Again, we'll see that on the next slide. Calorimetry just means heat measuring. So calorimetry is describing this general idea, this general technique of measuring heat of a reaction by measuring a change in temperature of the surroundings. So constant volume calorimetry is one of the types of calorimetry that we're going to talk about. So this is what a bomb calorimeter looks like. So the reason that it's a bomb calorimeter, presumably it could explode. I'm not 100% sure if that's why they call it a bomb calorimeter, but a bomb calorimeter is just a closed, sealed vessel. So we've got on the inside, this is our bomb. We've got a sample that's got oxygen added in as well, and we've got some ignition wires. So if we pass some electrical current through those ignition wires, then the sample burns. So we're going to burn our sample by blasting it with some electricity to heat it up, and we've got oxygen in there so that it can burn. Outside of that, outside of our bomb, which can't change in volume, outside of that we've got a bunch of water. And we've got a thermometer so that we're measuring the temperature of the water. We do the reaction, it releases heat. We've got a little stirrer in here so that our water's mixing, and then we can figure out after it's all done burning, what's the temperature of that water. And since we know the heat value for water, the C value for water, we can calculate the amount of heat that was absorbed by the water to raise its temperature. There's also some heat that can be lost to our calorimeter. So the calorimeter constant is the heat capacity of the calorimeter. Notice that it's not specific heat capacity, it's just heat capacity. If no heat escapes, so assuming that our calorimeter is good, that it's really well insulated, all of the heat gained by the calorimeter is going to equal the heat released by the reaction. So we're saying the heat is only going into the calorimeter, and the calorimeter is not losing heat to anything outside of it. So this should have some good insulation on the outside of it. So the energy gained by our calorimeter, the heat gained by the calorimeter equals the specific heat the heat capacity of the calorimeter times the change in temperature, which gives us our negative Q Rxn, the heat lost by the reaction. Heat lost during the reaction. And since no volume change is occurring, then the change in energy of the reaction is equal to the Q, the heat of the reaction. One of the reasons that we're using calorimeter constant, the heat capacity, not specific heat capacity, is because we're using the same setup every time. So you'd have to make sure that you're using the same amount of water. Most of the other conditions are almost identical. So we don't have to account for the mass of our calorimeter because it's the same unit every single time. So that saves us a little bit of work. I think we'll be calculating a heat capacity of a calorimeter today in lab. Okay, calculations. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 Celsius to 38.13 degrees Celsius. Find the change in energy of the reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So we've got a lot of stuff going on here. Some temperature values. We're looking for the change in energy of the reaction, specifically in kilojoules per mole hexane. And we're also given the heat capacity of the bomb calorimeter. So it would be helpful for us to pull these all out and list them on the side. So our temperature initial is the first temperature value, our lower temperature value in this case. Our final temperature, 38.13 degrees Celsius. C cal, run cal, run. 5.73 kilojoules per degree Celsius. If you forget what our equation is, which would be reasonable, or if you just can't figure out which one's the correct one to use, dimensional analysis can come to the rescue here. So our C-cal is kilojoules per degree Celsius. If we're looking for an amount of heat, we just need a degree Celsius value. We're given two values, so you might think, well, which one do we use? And hopefully you can remember we're doing a change in temperature. So our Q-cal, the amount of energy or heat gained by our calorimeter, is equal to C-cal times delta T. Should be our reaction or our equation. So plugging in some numbers, 5.73 kilojoules per degree Celsius, TF minus TI, our degrees Celsius will cancel. So we'll be left with units of kilojoules. So 5.73 times our change in temperature, (70.2498 kilojoules. This is a positive value. This is heat gained by the calorimeter. Where did that heat come from? What provided the heat that our calorimeter gained? The reaction. So our hexane that we burned, that underwent combustion, produced that energy. So Q-cal, that's the 70.2498 kilojoules, is equal to the opposite of the Q hexane. So that's negative 70.2498 kilojoules. Because our hexane lost the heat, so it's a negative value. Our calorimeter gained the heat, which is a positive value. So to find the delta E of the reaction in kilojoules per mole hexane, we have kilojoules. And we need to divide that by moles of hexane. So we're going to take our 1.550 grams, C6H14. We're going to divide that by the molar mass. So 6 times 12 plus 14 times 1, 86.178 grams per mole. So 0.01 and change moles C6H14. Shuffling things around a little here. Okay, I think this makes more sense. So the calculation to figure out the moles of our hexane, we're going to divide our kilojoules by those moles, and we'll come out with some value. And that value is big number. We'll call it 3,906 after we round up, and negative kilojoules per mole hexane. Questions about any of those parts? Yes.
So our slide says change of energy of the reaction equals the heat of the reaction. So would that be in kilojoules?
So the actual change in energy is the kilojoules amount that we found. So the actual amount of heat that was produced or gained, depending on which part you're talking about, 70 kilojoules. That's the actual amount of heat that was released. But the delta E for the reaction, just the general combustion, the general burning of hexane, we're expressing in kilojoules per mole. Because we know how much hexane we burned, so then we could, with this negative 3,906 kilojoules per mole hexane, we could predict, okay, if we burn half a mole of hexane, how much heat are we going to produce from that? Say if we're trying to produce a specific amount of heat.
Right, okay.
So that's where the utility of this value comes in. Other questions? Okay. We also have enthalpy. Enthalpy is H. So the enthalpy is a little bit more common if a chemical reaction occurs open to the atmosphere, meaning that it's not sealed off, it's not a bomb calorimeter. Energy can evolve as both heat and work. Like pressure volume work. So it's got room to expand, so it can expand, and it will expand. And the force that it's expanding against is just whatever our atmospheric pressure is. Often we're just interested in the heat exchanged and not the work done, so bomb calorimetry is helpful for that. But we also have enthalpy. Enthalpy is the sum of internal energy and the product of its pressure and volume. So H equals E plus P delta V. We're going to hold P constant. We're going to look at what if we change everything else. So we're going to add deltas in front of the rest of those terms. Enthalpy is a state function, meaning that only depends on final and initial values, not how you get there. And other state functions are internal energy E, pressure P, and volume. The enthalpy change, the change in H of a reaction, is the heat evolved in a reaction at constant pressure. So this H equals E plus PV. We've added deltas in front of the H, the E, and the V. We're holding pressure, constant pressure is not changing. and we can substitute in some values. So we know that delta E, our change in internal energy, is heat plus work. We're labeling this QP because we're at constant pressure. So Q plus W. And we know that P delta V, we're maybe getting some flashbacks. Work equals negative P external delta V. So if we swap that negative sign over, negative W equals P delta V. And so we can sub in negative W there. So work minus work, the works cancel. And so our enthalpy change is the heat at constant pressure, QP. Some fun math stuff that we can do. Yay, physics. Okay, so there's some differences in delta H and delta E. So enthalpy and internal energy change are similar in their concepts. They're similar in value most of the time. Delta E is a measure of all the energy, heat, and work exchanged with the surroundings, whereas enthalpy is a measure of only heat under constant pressure. So just to show those with the variables. So the difference between them generally is just the work, whatever pressure volume work might be done. So if the work is small, so if it's small work, then our delta E is about equal to our delta H, because the only difference is that change in internal energy has work involved in it as well. Questions about these concepts? Kind of math intensive. Okay. Lighters are usually fueled by butane, C4H10. When 1 mole of butane burns at constant pressure, it produces this 2,658 kilojoules of heat, and it also does 3 kilojoules of work. What are the values of delta H and delta E, change in enthalpy, change in energy, for the combustion of 1 mole of butane? This work is because you may know lighters store butane as a solid or as a liquid, and in order for them to burn, they have to be a gas, and so it's evaporating. So it does a little bit of expansion work. So what are our delta H and our delta E? I'll give you a little bit of time to think about those. All right, so some key issues here. We've got constant pressure. So we're working under constant pressure conditions. We're told that it produces this amount of heat and it does this amount of work. So heat is Q, and the number, just the magnitude part of that, 2,658 kilojoules. Is this going to be a positive number when we express it as Q, or a negative number? It's a negative number. And it's negative because it's producing. Producing sort of being the same as emitting. Right, we're burning it, it's releasing energy, it's producing energy, it's emitting energy, it's losing energy. So we can put a negative value in front of that. And then the work has a value of 3 kilojoules. And is this one positive or negative? This one is also negative. It does work. It's when you do work, you're exerting energy. It's the same for butane. So this one's also negative. So some things that are out right away. D is out right away because those are both positive numbers. And then we have to think about Q and W. On the previous slide, right, I wrote down delta E equals Q plus W, delta H equals QP. The QP meaning that we're in constant pressure conditions. We are in constant pressure conditions. And so our enthalpy, our delta H, is the same as our Q value. So this is actually QP, which means that it's also delta H. So we're looking for a delta H that has that value. Look, it's all of them. So that doesn't really narrow things down at all. But if we think about delta E being Q plus W, adding these negative 2,658 and negative 3 kilojoules together, 2,661 kilojoules total energy emitted. So adding these two together, it looks like the correct answer is C. All right, the signs of change in enthalpy and change in internal energy follow the same conventions. When the value is positive, heat is being absorbed by the system. So absorbed has a positive value, and we call those endothermic. Heat going in or being gained. When delta H is negative, heat is being released. So exothermic reactions, heat is released. Other words we might use to describe that are emitted, lost, produced. There's probably a couple of other things I haven't thought of there. So same thing that we were doing for delta E, our change in internal energy. Endothermic and exothermic still apply. So chemical cold packs typically contain ammonium nitrate. When that dissolves in water, it's an endothermic process. The way that those things get pulled apart, these ions get pulled apart, requires a lot of energy to be put in. And because it's an endothermic process, energy is being absorbed by the ammonium nitrate dissolving. It's absorbing heat from its surroundings, and so it's making everything colder. Absorbs heat from surroundings, which means that the surroundings get colder. Which might not necessarily feel intuitive or make a lot of sense. If we think about it in the opposite, though, the opposite of a cold pack would be a hot pack, like a hand warmer. Hand warmers are an exothermic reaction. They're producing heat. An exothermic reaction produces heat, releases heat. It makes the surroundings warmer because it's releasing heat. So if an exothermic reaction releasing heat, like combustion, releasing heat is making things warmer, then an endothermic reaction would make things colder. So it might be helpful sometimes to think for questions like this, if we were asking questions about this, what would the opposite do? So, okay, this is the system that we have. What would the opposite be? So we're asking about endothermic. What would an exothermic reaction do? Could be helpful. So it may be helpful to think about the opposite. for questions about things like exothermic and endothermic. Okay, let's identify each of these processes as endothermic or exothermic, and we can also indicate the sign of delta H just to get some practice relating endo and exothermic with our change in enthalpy. So an ice cube melting. When an ice cube melts, is it gaining energy or is it losing energy? It's gaining energy. It's going from a solid to a liquid. It's gaining energy. So that makes it endothermic. And since it's gaining energy, delta H is also positive. Nail polish remover, quickly evaporating after it's accidentally spilled on the skin. Or you could also think of like putting on hand sanitizer. And what's happening as it's evaporating. Is the nail polish remover or the hand sanitizer gaining heat or losing heat? Does it make you feel cold or does it make you feel hot? Yeah, it's gaining heat. It makes your hands feel cold because it's stealing your heat. It's stealing heat from your hands, so your hands are losing heat. That heat is going into the hand sanitizer, into the nail polish remover to cause it to evaporate. So it steals/gains heat from skin. So this is also endothermic. And so delta H is positive. What about gasoline burning in the cylinder of an engine? Or just gasoline burning in general? Is it producing energy? Is it absorbing energy? It's producing energy. So it's producing energy, which means that it's losing energy or emitting energy. So this is exothermic. And what would the sign for delta H be? Is it positive or negative? It's negative, because the gasoline is losing energy. All right, zooming into the molecular level. An exothermic reaction, like burning something, gives off thermal energy. Where does that energy come from? We know that internal energy equals kinetic energy plus potential energy. It's not a change in kinetic energy because the temperature would be changing. The temperature is not changing. It's not like rapidly changing in temperature when we're doing this exothermic reaction. The source is actually potential energy. And the potential energy in this chemical reaction is chemical potential energy. So what's happening in exothermic reactions is that weak bonds are broken. In order for us to break bonds, you could think of like cutting pieces of rope. It takes energy to cut rope. It takes energy. You have to put some energy in to break the bonds. So there's a little bit of energy that's required. So like a lit match or a lighter. Right, you're providing a little bit of energy, a little bit of a starter, and then that's enough to break some bonds. And then strong bonds are formed. Strong bonds are stable, and stable bonds, stable things are low in energy. So we break the bonds, we separate the molecules, and they've got relatively high energy. Now we've added some energy in, so they're in this high energy state. When they reform those bonds, they're settling in to a low energy state. And that extra energy is then emitted. And this probably feels very unintuitive for most people. So when these strong bonds, these stable bonds, these low energy bonds are formed, the low energy of the system bonds, we're releasing a large amount of energy. So we use a little bit of energy in the form of a lit match or a lighter to start like a candle or an engine or a fire. And then we get lots of heat out because of all of the bonds that are being broken and reformed. In endothermic reactions, strong bonds are being broken. Since they're strong bonds, it takes a lot of energy. A lot of energy input. And weak bonds are formed. The weak bonds are less stable. Not as much energy released. Again, so weak bonds, it doesn't take very much energy to break them. So in an exothermic reaction, weak bonds get broken by a little bit of energy input, and then they form strong bonds after they're broken. So they reform as things that have really strong bonds, and when those bonds are formed, they release energy so that they can settle into those strong bonds. Endothermic reactions are the opposite. So let's say that an endothermic reaction occurs in a flask. What happens to the temperature of the flask? Does the temperature rise? Does the temperature fall? Does the temperature stay the same? What's the energy exchange for the endothermic reaction? We've got something happening inside the flask, an endothermic reaction. What's the endothermic reaction mean? Is it gaining heat? Is heat going into the reaction, or is heat coming out of the reaction? It's gaining. It's going into the reaction. So it's absorbing heat. The reaction's absorbing heat. Where's it getting the heat from? It's getting the heat from the flask, or the contents of the flask. So what does that mean about the contents of the flask or the flask itself? It's losing energy, and so it's going to have the temperature go down. So the flask/contents lose energy, temperature goes down, so the temperature falls. We could also think of it in terms of the bonds that are being changed. So there's strong bonds that are being broken, really stable bonds that are being broken. So you have to pump in a lot of energy to break those bonds. And then when bonds form, they release energy. We're forming weak bonds, and so there's not as much energy coming out as the amount of energy that we put in. That's probably the better way to think about it, but it also works thinking about it the way we did the first time around. Questions about any of all this? So again, this is a case where thinking about the opposite can be helpful. So thinking about bonds. If we're breaking bonds, I think it makes sense for most of us. If we think about breaking bonds, okay, you have to put energy into breaking bonds. The opposite of breaking bonds is forming bonds. And if we have to put energy in to break bonds, then energy must be released to form bonds. So I'll write that here. It takes energy to break bonds. Energy put in. I'm going to rephrase that. Breaking bonds takes energy, absorbs energy, so forming bonds, the opposite, I missed the bonds part of that sentence. So forming bonds releases, emits energy. And we'll go ahead and stop there. Any questions? Okay.